And it's locked up, isn't it? We'll get started sooner or later. I wonder if it's working. I don't know, we'll go with it. Anyway, it's 13.3 circular approach. So you've got a circle drawn in front of you. Inside that circle, a triangle is drawn. The angle starts here, rotates to the terminal side, that was Friday's lesson, and it intersects the circle at some point xy. Now the triangle I drew in is not actually there, hence why this is dashed. This isn't a real triangle, it's actually not part of the diagram. But you can use that to come up with trig ratios on circles. To get to this point xy, how many units did you move right? There's no numbers. You moved x units right. This is abstract thought, no numbers. You moved x units to the right. How many units did you go up? Y. X is left and right, y is up and down. Now, you can cycle through SOHCAHTOA and use this triangle for a circular approach. From SOHCAHTOA, what's the sine ratio? Look at your triangle. What's opposite of the angle theta? Y. And what's the hypotenuse? R. Label as R. The sine of an angle is y over the radius of the circle. SOHCAHTOA, what's the cosine ratio? Adjacent over hypotenuse. So we look at our little circle here. What's adjacent? X over R. Cosine is X, sine is Y. Tangent, opposite over adjacent. That's right.
So that's y over r. Y over y.
No R's.
X over y.
Y over X.
X is not adjacent to theta.
Tangent is opposite over adjacent.
So CSC would be h over a equals r over y?
Hold on a second. Wiley, you see your mistake? What's the cosecant ratio? O. Cosecant is O. Sine says O. Cosecant is a ho. So what's the hypotenuse?
R over y.
R over Y. Secant is the funny guy.
R over x.
R over X. And last off's cotangent.
A over o equals h over y.
Now, all you get from that ordered pair is the x's and y's value. You still got to find the radius of the circle, R. That's what the next question is about. How do you find the radius? What theorem do you use? Pythagorean. You can literally just write down x squared plus y squared is r squared. I usually take this a step farther on the circular approach. You want to know what r is, so how do you counteract squaring? Square rooting. Take the square root of both sides. Can you take the square root of x squared plus y squared? No. That's how you find r. R is the square root of x squared plus y squared. That's all the stuff you got to memorize for the circular approach. Only one quiz too, isn't it? Yep. It is. God, it's so slow. Probably.
Good spring break this year.
I worked every day in that crappy weather.
Me too.
You work inside.
Yeah, but I worked 52 hours, dude. Yeah. Having drunk tests, going through the drive-thru, spit beer in my face. Oh no, other place I'd rather be than
You had a darkness fit.
Yeah, it's recording. An angle terminates at the coordinates -3, -2 on a circle of radius 12. Evaluate the 6 trig ratios for the angle. Use your circular approach. How do you find the sine of an angle? call it theta.
Opposite over.
No, with a circle. You just wrote it down.
However,
Wow, we're R.
However, R, you just took the notes, Ryan.
sorry.
That's all it is. If you look at the ordered pair, what's the y value?
-2 over 12.
There you go. You can do better than -2 over 12.
-1.
It talks about being on a circle, doesn't it? The circular approach.
So that's all we did.
Yeah. How do you find the cosine of theta using the circular approach?
H over R.
X over R. It's -3 over 12. What's that reduce to?
-94.
I don't want to do all of these things. Let's just do randomly. Let's do secant. I don't want to do all 6.
1 over X.
Yes, secant is R over X. That'd be 12 over -3, which reduces down to
-4.
4. That's the nice thing about circular approach. It's easy. Especially if we give you radius. And they did. This one doesn't talk about being on a circle. It doesn't matter. Is there an order pair given? You can pretend there's a circle. You can. This says the angle stops here. Now, in order to use your circular ideas, what do you have to know? You have to know the radius. Find it. How do you find it? What's the formula for finding a radius? You wrote it down.
On this paper?
Yes.
X squared plus 1. Oh, yeah. X squared.
Just plug numbers in there and go with it. That's all you do. You're going to square a number. Does the sign matter?
No.
So if you do 4 squared plus 2 squared, what do you get?
16 plus 4.
Which is?
16 plus 20. Square root of 2 squared. And then it's going to be R.
We're not done with this. That's right. If you've done your homework or whatever, taken tests in here, this has been simplified 100 times. It's 2 root 5. These are going to require a little bit more work than the last ones. They are. Again, I don't want to find all of them. Let's just do maybe 3 of them. Start with sine. Using a circular approach, what's the sine ratio? Y over R. Y value is 2. What's the radius? So when you guys did a little SoCal with Miss Cantrell last year, you played red box, green box. That answer would be what?
That answer would be correct.
Wrong. It's a red box.
Red box.
You have a radical in on there. Plus it can be reduced. What's 2 over 2?
1 over.
Negative square root of.
I don't know where the negative came from. Unless you're looking at X. That's 1 over root 5. Would you get a red box or green box for that answer? Yep. Do you know why? Nope. Radical. You're not supposed to leave radical numbers in the denominator.
So we have to find the square root of it.
No, Ross. We don't want decimals either. How do you what do you multiply top and bottom by so that root 5 is not in the denominator? The denominator, root 5. Multiply the bottom by root 5. Multiply the bottom by root 5. You got to do it at the top. That was done with you all last year. It was. It was only algebra 1 too. Up top, that's 1 times root 5. Root 5. Down low is a radical times itself. You multiply a radical by itself, what do you get? You get 1. You get the number inside. Root 5 times root 5 is root 25, which happens to be 5. Multiply a radical by itself, you always get the number inside. Years and years of calculators done that to you. Next up is the cosine ratio. From the circular approach, what's the cosine ratio?
X.
X over R. That's -4 over 2 root 5.
Or we can do it simplified.
How?
-2 over root 5.
I agree with that. And then how do you clean that one up?
Multiply by root 5.
Over.
Root 5.
When you multiply by root 5 over root 5, what are you really multiplying by? 1. You're not changing the number, you're changing the way it looks.
So it would be -2 root 5 over 5.
Yep. Somebody a long time ago said no radical numbers in the denominator. Let's do a random one. Let's do cotangent theta.
So
Circular approach.
X over Y.
Cotangent theta is x over y. What's the x value? Y values. There you go.
So it's negative.
Negatives. Circular approach is not hard. It's probably easier than SOHCAHTOA.
I don't know. That was easy.
Yeah, but you don't have a triangle that you're drawing. You know, a lot of kids can't do opposite adjacent. I'm not sure why, but a lot of kids can't. Circular approach requires memorization. That's what it requires. What's up next? Talking about a reference angle, because this is about to come up. Before we talk about a reference angle, we need to do this one. We're going to do this one, then we'll go back to know about the reference angle. I think I changed the numbers on this one. No, this one's the same. It's the next one changed. So the same type of question from a non-circular approach. So you can do exactly what we've been doing by simply drawing. Just draw the x, y axis. 3, -4 would mean you go right 3 and down what? 4. It'd be a point somewhere in quadrant 4. That makes sense? You can grid out the x and y axis if you want. It doesn't matter. Now what happens is the angle starts here, rotates, stops there. When you draw an angle, what you hopefully see is two sides of the triangle. You can just connect this little point right here to the x-axis. Bam, you've made a right triangle. Haven't you? To get to this point, how many units right did you move? 3. You moved 3 units right. And then you fell 4. Seems really weird to put a negative length on a triangle. The triangle's not really there. I'm not saying the triangle has a length of -4. I'm saying to get to that point, I fell 4. There is no triangle. The triangle is there so that you can use SOHCAHTOA. That's what the triangle is there for. So you can use SOHCAHTOA.
So the square root of 3 squared.
You can still use that. If you want to find the hypotenuse, you can still do. There's no, we're not going to say R. We'll just say C, square root of what?
3 squared minus 4 squared.
Plus, it's going to be 5. Cantrell made you memorize 3, 4, 5 patterns, didn't you? Hypotenuses are always positive. Now, then approach this from circular approach. We're going to use plain old SOHCAHTOA. Nothing more. So let's do something like cosecant. Cosecant is a reciprocal of sine. Sine is O over H. So what's cosecant? We're not doing a circular approach. I didn't draw a circle. Didn't find a radius.
So it's just going to be H over L.
Cosecant is a hoe, kids. Do young males not like hoes anymore?
I know a lot of cosecants.
So what's the hypotenuse of a triangle?
Usually cosecant.
We don't call men hoes. There's another word for them. Hypotenuse is 5. What's opposite of?
-4.
Something I didn't reference, and I'm about to. There's the angle. What's opposite of it? -4. Done. Pick a ratio you want to find, there's 6 of them.
Let's do. We haven't done tangent yet.
Tangent's fine. From SOHCAHTOA, what's the tangent ratio? Opposite over adjacent. So here's your angle. What's opposite of it? What's adjacent to it? 3. Do one more. I don't want to do all 6. Secant. What do you know about the secant ratio?
Hypotenuse over there.
I know some kids don't get that. Secant is reverse of that. This is cosine. Secant's reverse of that. Cosine's A over H. Secant's H over A. That was taught to you guys last Thursday, the Thursday before last. But secant is the funny guy. Ha. So what's the hypotenuse? There you go, 5 over 3, 5/3. It's not hard. You can use a circular approach or you can go back to SOHCAHTOA. SOHCAHTOA is a little more work. With SOHCAHTOA, you have to draw it, don't you? You have to draw it. Now, I don't know, it kind of got a little lost on the board when I drew it. The original angle here probably would have been called theta. This is the original angle. Theta starts here, rotates to there. I actually wrote inside the triangle something called theta prime. It's called a reference angle. I referred to that little angle for the actual angle. That is a reference angle. So I skipped over the slide talking about reference angles. I don't know if this makes any sense, but I didn't actually use anything from the original angle, did I? I drew a new angle, didn't I? And used it. So back on the slide, I skipped over definition of a reference angle. Reference angle is the angle formed between the terminal side of an angle and the closest x-axis, and we use prime notation, which you did use last year. So if the original angle is theta, reference angle is theta prime. Here's why it works. Reference angles have the same 6 trig ratios as the original angle. Next down there it talks about the arc functions on the calculator. The Thursday before spring break, I had you guys press the arc buttons on the calculator. Probably don't remember that, but you did. The arc functions on a calculator return reference angles. And here's the truth about them. They only work in quadrant 1. Cosine works in quadrant 2. They only really work in quadrant 1. This is a problem. They only really work in quadrant 1, and you're drawing angles all over the place. How much can you trust a calculator? 1/4 of the time. It actually ends up being a little higher than that, but about 1/4 of the time you trust a calculator. So the arc functions on a calculator, with the exception of arc cosine, return reference angles that may or may not be in the same quadrant as the angle you draw. So the next slide that we're going to look at is about using a calculator. So if you don't have a calculator, you're going to need one. You know what Greek letter that is? Alpha. Jesus fish. Alpha. Angle alpha terminates at -4, -1. I changed that, by the way. Yours says -4, -2, doesn't it? I changed it to -4, -1. What quadrant is that in? It's not the 4th quadrant. It's the 3rd quadrant. It's right here. Do you guys want to do this using SOHCAHTOA, or do you want to do it using the circular approach? Okay, circular approach is fine with me. If you use a circular approach, that means that this point terminates on a circle. It's at -4, -1. Now, on which axis do all angles start?
X.
Positive X. And then they rotate to the terminal side. You want to take a guess at the measure of that angle?
Which one's 90? So it's 90. 180 is going to be about 215.
That's the closest one I heard. So guess is roughly 215 degrees. That's what it was. It was a guess. Right? It's fine. That's what I want to do. At least realize how big the angle might be. Now, what are we supposed to do here? We're supposed to evaluate the first 3 trig ratios for this angle, then use the arc functions to find the measure of the angle. And Hayden suggested the circular approach. That's what we're going to do. Hayden suggested a circular approach. If you want the sine of an angle, in this case it's the Jesus fish alpha, using a circular approach, what is it? First slide of your notes, circular approach. Circular approach was suggested. That's what I'm going to go with. Y over R. What do I still need to know?
The radius.
Radius of the circle. How do you find radius of the circle? Over the shortcut, which is Pythagorean theorem, by the way.
What do we call it?
X plus Y.
X squared.
X squared plus Y squared.
This stuff isn't hard if you're willing to sit down and memorize.
R equals, R equals 4 squared plus 1 squared,
Which is
17.
root 17. So now I can do all this stuff. If I want the sine ratio, what's the y value? -1.
Over
Oh.
root 17.
Problem with that answer?
There's a,
Radicals problem. How do you clean up root 17 in the
times
denominator?
root 17.
Wiley, you said something silly the first time. Let's see if you fixed yourself. What's the root of 17 times root of 17? 17. A radical times itself is whatever's inside.
So negative root 17 over 17.
So this one ended up being kind of funny looking. Negative root 17 over 17. Let's see, it says the first 3 trig ratios, so I guess next is cosine. Using the circular approach, what might be the cosine of that Jesus fish feed? X over R.
Is that a alpha sign?
Alpha, yeah, Jesus fish. The alpha symbol is a Jesus fish. Yes.
What is that?
No, it's the Jesus fish. Just the font it's written in. Anyways, what's the X value? Radius is still root 17. Same problem. Putting them up by top and bottom by.
Root 17.
Root 17. What's that cleanup look like?
Negative 4 over 17 over 17.
All right, that one is done. And lastly, we need tangent using a unit circle approach. Not a unit circle, a circular approach. Y over X. Y over X. That is right for tangent. So what issue? 1/4. What we're going to do is we're going to do the arcs of all these numbers. I didn't leave myself enough room to actually write in those blanks. We're going to press the arc functions on the calculator and see what they say the angle is. Remember, we thought the angle was what, about 215? None of them are going to be right. Whatever you calculate is going to be entirely wrong. Those things only work correctly in one quadrant. One. Now, do you want to work with degrees or radians? What are you more comfortable with, degrees or radians? I would check and make sure your calculator's in degree mode. This one wasn't. I have to change it. Arrow down, highlight degree, and press enter. And I quit out.
Wait, so we can do 4,000 degrees?
No, I use this calculator in other classes, Ross. The first thing we're going to do is the arc sine of what?
Sorry.
What was the ratio we had? Arcs return angles. Negative 14.04 degrees.
Oh, I got,
Nowhere near 220, 215, is it?
I got a 9. Good, shorter than the second sentence, just. I don't want
Ross, there's how I type it in. Wonder what cosine is. Our cosine was negative 4 roots of 17. Sitting pretty over 17. 165.96. Closer, but not right.
how do you get the name clear thing?
Why are you trying to figure the memory?
The word clear a lot of stuff out, so I'm gonna clear it off.
Ross, I need you here. I don't care what's in that calculator. You shouldn't either. Got 165.96 degrees. Is that the right answer? No. The thing's obviously more than 180, is it? All right, arc tangent's going to give you probably positive 14.04 degrees. What was the arc tangent of what, a quarter? 14.04 degrees. None of those answers make a bit of sense. None of them. Here's why. If I can ever get to that page. Oh, please don't freeze. It says the arc functions on a calculator, they only work properly in part 1.
Obviously.
And with the exception, and it should say with the exception of arc cosine, they return reference angles. That's all they do. Return reference angles. What do I mean by that? A reference angle is formed to the nearest x-axis. So I'm going to draw these reference angles. I'm going to draw the original angle. This is the original. It stopped. I don't even know why it switched over to eraser mode. It stopped about right here. We did the arc sine of negative root 17 over 17. And we got about negative 14.04 degrees. I was to draw that angle. Would it rotate like a clock or counterclockwise? Counter. It would rotate about like that. And it would have a negative rotation, 14.04. Did our cosine of negative 4 root 17 over 4, I think. It was what, 155.96? No, 165.96. So it would rotate about right there. That's not a reference angle. How many degrees in a straight angle? 180. How do you find that missing little piece right there?
Or I subtract that from 180.
Yep. That missing piece is 180 minus 165.96. And guess what that is?
14.04.
14.04, that's the reference angle. The other one we did was we did the arctangent of a quarter. And we got 14.04 degrees, which would look about like that. Go back to the original. What do you believe that little sliver is there? What the calculator gives you is it gives you numbers you can use as reference angles. It gives you a reference angle is formed between the terminal side of an angle and the closest x-axis. That was the whole point of doing this. So you can maybe figure out how to use what the calculator gives you to make sense. So the actual measure of the angle is 180 degrees in the semicircle that was covered, plus 14.04.
So
194.04 degrees. So something that bothers kids in trig and algebra 2 is that the calculator is not to be trusted. What else do you have to use? Yeah, use this thing. And I wouldn't call it common sense.
Yes.
But your brain has to be used to this. Plain and simple. One more of these. Angle theta terminates at -3,2. Evaluate the first three trig ratios for the angle. Then use the arc, the inverse functions terminating as measurement. You want to do circular or you want to do SOHCAHTOA?
Okay.
That's fine. Do the last one circular. Do this one SOHCAHTOA. This is angle theta. It's theta. It rotates so that it terminates at -3,2, which would be back some and up, right? Now I'm going to draw in the imaginary triangle. Triangle is not really there. To form that imaginary triangle, how many units left did I go? I went left 3. If you're going left, that's negative. And you went up what? 2. Again, Ross wants to use SOHCAHTOA, which is not a problem. But to use SOHCAHTOA, I don't need to know the radius. What do I have to know? I have to know the hypotenuse, right?
So 4 plus 9.
He's doing Pythagorean theorem.
13 squared root of 13.
C is the square root of x squared plus y squared. Same thing. So 2 squared. Signs don't matter when you're squaring. Plus 3 squared. Then you got root 13. Do we want your decimal? No. Nobody. This was theta. There is no triangle associated with theta. There's a triangle associated with a reference angle called theta prime. Really?
So you're spending so much time for computer.
Oh well, you've seen enough. That's crazy. I finished that in the second period. Probably because I was waiting on the computer for so long.